So far we have been talking about primarily the performance part of a CPU usage, right? We want the CPU to be doing useful work. But for an embedded system especially, one of the key metrics of interest is power, right? And power, as we have seen earlier, power actually directly translates into the heat generated by the system, but it also has an impact directly on the lifetime for which a system can operate, especially for a handheld or battery operated device. So let's look a little deeper into the power considerations when we are actually building an embedded system. The first question is, what causes dissipation of power, right? And in electronic systems, there are two broad classes of power dissipation that you need to be aware of, right? One of them is so-called dynamic power. And what happens in dynamic power is, every time that a transistor inside the circuit switches, right, from 0 to VDD or back, any signal, any wire, when it is switching from 0 to VDD or back to 0, there is essentially a movement of charge. There are some internal capacitors, right? Any metal wire at the end of the day in some sense has some capacitance associated with it, because it's metal, there is some kind of insulation, and then there is a ground plane. So just relative to those, you can imagine that there is a kind of capacitance involved, which means that changing the voltage of a wire from 0 to VDD is not, as we would like to imagine, something that can happen instantaneously. It actually takes time to charge. Now the problem is, every time I need to charge something up, it means I am drawing current from my supply, and that charge now sits on my capacitance and after some time gets discharged back to ground, right? And the more such activity that I have, the more number of times that I have gates or capacitors or some electronic elements inside my circuit switching their voltage values, right? I can imagine that more energy is being drawn, right? Or more power, in other words, is being drawn from my supply, because energy per unit time, the more number of transitions per unit time, the more energy per unit time or the more power is being drawn from the supply. In general, as a rule of thumb, you can imagine that if your circuit has more transistors or gates, logic gates in general, right, it's a more complex circuit, and in general that would imply a larger power consumption. Okay, this is not obviously always the case. There might be scenarios where I have a large circuit but most parts of it are not toggling, but that's unusual. You don't build large circuits and then not use them, right? The second thing is, as you can imagine, the higher the frequency at which your circuit is operating, the more transitions per second you are going to see, which in turn translates into a higher power consumption, right? Now all of this essentially falls under the category of what's called dynamic power at the circuit level. Now there are also something called short circuit currents which happen during the transition as a particular gate is switching from 0 to VDD and vice versa. It also falls under the category of dynamic power dissipation, but I'm not going to talk any more about that right now. It's definitely at a slightly lower level than this primary activity based switching that you have, and you can probably sort of club this along with the other switching activity for the most part. The key point over here is, this dynamic power is directly dependent on how much your circuit is toggling, which in turn at a very intuitive level can be thought of as how much work you are doing. Now on the other hand, we also have something called static power, right? And static power dissipation is essentially current that flows from the supply down to ground even when the transistors or the logic gates are supposed to be off, right? Now when you go through your first course on digital systems, the intuitive, and you are not even thinking in terms of currents and voltages and so on, you are just thinking in terms of zeros and ones. The point is, each of those gates is actually implemented in terms of actual transistors and circuits, and what happens in practice is, when you wire them up, no matter how good your technology, there is some amount of current that leaks, right? Because there is no such thing as an infinite resistance. You can only have very, very high resistances, right? Which hopefully prevent any flow of current, but for anything that needs to be turned on at some point, it's very unlikely that you will be able to turn it off so thoroughly that it absolutely does not let any current at all flow through. The current that flows might be orders of magnitude less than the current that flows when you actually turn it on, but it doesn't matter because it is always present, right? So this leakage current that we are talking about when transistors are off, as long as you have power connected to your system, it is always leaking. It doesn't matter whether you have tried to shut down the various parts of your system, you are not toggling, your clock has been turned off, it doesn't matter, there is still some amount of leakage that's happening. Apart from that, many of these systems are built to use batteries, and batteries themselves have an internal resistance which hopefully should be such that the leakage through the internal leakage of the battery should be as low as possible, but it is never completely zero, which is why even if you take a battery and just leave it idle, right, without connecting anything to it, but you leave it for a few months, it's very likely that some amount of the charge stored on it has drained away, right? Almost certain that some amount of the charge on it has drained away. And if it's a poorly built battery, it might have completely drained in the time that you have left it out. Certain kinds of batteries like the coin cells used in watches and so on are very well designed to have really long lifetimes. They have like really low internal leakage, which means that they are designed to run for possibly even years, right? But nevertheless, batteries do leak, and over time you are going to lose charge. The point about static power and in general leakage power is that it is always present, which means that it doesn't matter how efficiently you write the rest of your code, there is still some amount of energy being drained away just by powering on the system in the first place. There are tricks that can be used in order to reduce this leakage power. There are circuit level techniques called power gating, sleep transistors and so on, but all of them can at most try and reduce the leakage, never completely eliminate it. Now, that was at the circuit level. Now, as an embedded system designer, you are probably going to look at the component level, right? And what are the components in an embedded system? You of course have the core, the CPU itself, along with any on-chip peripherals that might be there, and of course the clock circuitry that actually provides the functionality, the clock signal to the entire circuit. And it turns out that the clock signal is actually a major consumer of power in general, right? Now, with all of that, apart from that, you also have the I/O, the peripherals, right? And not just the peripherals, also just the pins associated with the chip. It turns out that the moment you want to drive a signal out of an integrated circuit, out of the chip, you have to go on to electrical wires that are significantly larger than the wires that are there inside the circuit, which in turn means that they are fairly high capacitances, right? And they tend to consume more power. So anything where I need to sort of activate the pins and communicate with the outside world tends to consume more power than if I am able to do things completely inside the chip. What about memory? Anytime I need to store data, yes, there is a large amount of data being stored and retrieved from some chips similarly, right? And the very fact that I need to sort of sense that data and get it back means that there is a lot of toggling activity, right, which in turn translates into power. Peripherals, the sensors, actuators, communication that are the sort of the bread and butter of embedded systems are all at the end of the day dealing with data. Data in turn means toggling, and that in turn means that you are actually going to end up consuming power. In a lot of embedded systems, the display unit is actually one of the biggest power sinks that you have, right? Because you need to actually have a screen that is continuously getting refreshed several times per second, right? Typically 60 times per second or sometimes even more. And you want to have a fairly bright output, right? You want it to actually be visible under a lot of different lighting conditions, which means that you actually have to pump current into the LEDs in order to make them glow. And that ends up being, in a lot of cases, even more current than the rest of the system put together is going to draw. Right? Now, apart from all of these, you also have the so-called power management circuitry in the first place, right? Because there are some chips whose job is simply to make sure that you have a stable and reliable power supply to the rest of your components. Now, you might think initially that after all they are the ones providing power, why would I consider them as wasting power? but it turns out that just those chips themselves have internal power losses, right? And of course, there are ways of sort of minimizing those losses, but the fact of the matter is that they do consume a certain amount of power on their own. Now, the key point that I am trying to make over here is that just having a low power microcontroller by itself is not sufficient when you are trying to design a system. This is system level design. Every single one of these components needs to be monitored, and you need to understand where the power might be getting dissipated. And unless you actually target the bottlenecks and figure out which are the ones that need to actually be reduced, you are not going to successfully improve your overall design's power consumption. Now, CPUs generally provide you with multiple modes of operation, and the reason for this is twofold. One is that people spend a lot of time designing CPUs, right? And there are ways by which they say, okay, let's try and squeeze everything possible out of what a CPU can do. And the second is, even though I said displays tend to consume a lot of power, the CPUs, especially when they are trying to perform computations, are probably the most power hungry part of the system, apart from the some things like the display or sometimes the communication modules, right? So it is well worth trying to optimize them. And in the case of CPUs, the approach that is taken is you provide multiple modes of operation. The most common one is, of course, or the most important one is the active mode, where you typically have the highest power consumption, but it also means it's operating at the highest frequency and is actually meant for being responsive and to perform computation. Now, not all systems are performing computation all the time, which means that you would have idle power modes, which could be something as simple as a no operation being repeatedly performed, or it could actually start shutting down peripherals one by one, right? Anything that's not actually actively required at this point can go into sleep modes. Now, keep in mind that even in sleep modes, leakage power is still present, but that's typically orders of magnitude less than the active power. So, if you can figure out how to sort of take your CPU and put it into a sleep mode for a majority of the time, you probably have a net saving in terms of the power consumption. Now, there are CPUs, the TI MSP 430 series being sort of famous for this, where there are ultra low power modes, right, where the CPU by itself consumes so less power that you could build things that run for months if not years on a single small battery, right. Designing for such systems is not trivial, but is also something that has been well studied, and by sort of following best practices recommended by the manufacturer, you should be able to get very good battery lifetimes. Now, how exactly do you estimate something like battery lifetime? Let's take a specific example. Now, this is a completely artificial made up example that I am considering out here, but it serves the purpose and sort of is meant primarily as an illustrative example out here, right. Let's say that I am building a system, and the major components that I have over here are the microcontroller unit, a sensor maybe that is actually reading data on a regular level, logging it into some internal memory, and a radio. This could be Bluetooth or Wi-Fi or something of that sort, that periodically sort of needs to transfer the data to a system, right, to a central monitoring system. Now, each of these components, of course, there would typically be other components, the charging circuitry at the very least, right, possibly some other kinds of low speed or low power peripheral for communication, maybe a UART or something of that sort, which is generally used only for debugging. Maybe some LEDs on the system that occasionally glow just to sort of show some status, right. But the point is, these, at least at a first cut, are the primary sources of power consumption that I can think of, at least, okay. So, what we have over here is, I have these numbers, active power and sleep power, right, and I am sort of oversimplifying the problem. I am going to assume that at any given point in time, each of these components is either active or it is sleeping, right. And the duty cycle over here is a number which basically says, out of, let's say, a total of 100 seconds, every 100 seconds, what percentage of the time is that particular unit actually active. What this says is, out of every 100 seconds, the MCU is going to be active for about 20 seconds, right. whereas the sensor is only going to be active for 5 and the radio is only going to be active for 2. Now, how is that possible? Well, the sensor is something which maybe wakes up only once every 20 seconds, right, and is awake for 1 second, during which time it basically senses something, and therefore it has a duty cycle of only 5%. But now once the data has been sensed, the CPU or a MCU has to do something with it. It has to do some kind of processing, due to which it actually ends up being awake 20% of the time, much longer than was required for actually activating the sensor itself, right. And finally, as you might notice, the radio is actually active for a very short amount of time, and the reason for this is maybe the processor has already done some kind of compression or some other coding of the data or processing of the data, and the only thing it needs to do is activate the radio very briefly in order to blast that data out to whoever is logging the data. This is a very common sort of usage scenario. Now, in practice, it's not as simple as this. You might actually have multiple power modes between which you need to switch. You might not be able to go straight away from active into just one sleep mode. You might have deep sleep modes. You might have other kinds of sensor modes as well. There might be a wake up time, there might be charging currents that are initially associated with it, but this gives you a flavor of the kind of things that you are actually expecting to see. Now, where do these numbers come from, the active power and sleep power? They typically come from data sheets, right? And knowing how to read a data sheet and get power estimates from there is a very important part of how you go about doing embedded design. Right? The duty cycle, on the other hand, typically comes from the program profile, because you as the programmer get to control when the CPU goes into sleep mode, when the radio wakes up and transmits, when are you using polling or interrupts in order to get data from the sensor. All of that can make a difference to the kind of duty cycle that I see for the different units. Now, what we want to do is to actually perform an average power calculation out here. And as you can imagine, I want to spend as much time as possible in sleep mode, right. The other thing that you might notice is that the radio actually consumes more active power than the MCU, and this is in fact quite common, right, which is why we typically try to operate radios or the wireless communication systems in burst modes. I put them into deep sleep mode where they consume very small amounts of power, wake them up very briefly, blast out a packet of data, go back into sleep. Try to keep this duty cycle as small as possible so that the average power becomes low. How do we compute the average power? Right now it's very simple. If I know that the duty cycle on the MCU is 20%, I basically take the 50, multiply it by 0.2, which is 20%, and the sleep power 1 milliwatt into 0.8, the remaining 1 minus 0.2, right, the 80% of the time it's in sleep mode. What this means is that my average power, averaged over time, right, is 10.8 milliwatts for the CPU alone. Right. Now, the interesting thing that you need to keep in mind over here is the peak power that's actually being drawn, that can be drawn from the system and that the battery should be capable of delivering if required, is 50 plus 10 plus 100, assuming that all three are in their active mode, right. So, the battery has to be capable of delivering enough current to be able to handle temporary spikes where all three of them are active. But if I average things out, I will find that the average power from the MCU is only 10.8 milliwatts. The sensor is even better. First of all, it has a lower active power. It also has a much smaller duty cycle, which means that the sensor actually is only consuming around 0.6 milliwatts on average. And the radio, interestingly, even though it has such a high active power, because I have managed to keep the duty cycle so low, ends up consuming only an average of 2.5 milliwatts or so, which means that for this particular system design, I still end up with the MCU consuming the maximum average power, right, which means that if I could figure out some way of optimizing and getting my duty cycle even below 20%, I would definitely benefit. On the other hand, if I go and try to optimize this sensor and say, okay, I'll reduce this 10 milliwatts of active power by getting a better sensor, it's not going to make any real difference to your final design, right. And interestingly enough, if I then go and put an LED on this system that is always on, and let's say consumes 10 milliamperes of current, right, I would suddenly probably find that that ends up consuming more power overall than everything over here put together, right. So, when you are designing the system, something which you thought was very tiny, an LED which is just sitting there in the corner not doing anything, well, it is on, which means it is drawing current, and over time, given the fact that it is always on and never goes to sleep, could end up actually consuming more power than the rest of the system put together. Now, it is simple, we basically add up all of these numbers and we end up with an average total power of 13.885 milliwatts. But you need to keep in mind that these are estimates at best. When somebody says that the active power of the MCU is 50 milliwatts, it does not mean 50.0 milliwatts or 50.00 milliwatts, right? It is not accurate to that level. This is a rough estimate, which means that when you are reporting the average power also, you need to keep that in mind. At best, you could say that 13.885 milliwatts is about 14 milliwatts, but in practice, you can probably say that, hey, this is somewhere around 10 to 15 milliwatts of average power that this thing is going to consume. Okay. Alright, so this gave us an estimate of how we can use the program information as well as data sheet information in order to find out an average power number, right. Now, with that, the next step would be, okay, I am trying to build a battery operated system. This is a typical battery that I just searched for and found on one of the robotics websites where you can just buy it anywhere. It's about a few hundred rupees or so, right, and it's a very common kind of battery used for the embedded applications, right. As you can see, the specifications on it say that it's a 3.7 volt battery with 400 milliampere hour of storage. Now, this is a slightly strange way of giving the storage capacity of a battery. Ideally, I would want to know how many milliwatt hours can it store, right? But the point is that they are actually making a lot more information clear over here. What they are saying is that the rated voltage that comes out between these two terminals is 3.7 volts. And at that voltage, if you were to draw, let's say 400 milliamps, the system would last for 1 hour. If you were to draw 40 milliamps, it would last for 10 hours and so on, right? But keep in mind that that is at best a first level approximation. If you really want to know how the thing would behave, you need to go look at it a little more carefully. And the reason I say that is, if you were to actually draw 400 milliamps of current from this battery, most likely it would drain in much less than an hour, because even though it has a total capacity of 400 milliampere hours, that is usually at some rated current draw. Okay. On the other hand, if you draw, let's say, only 4 milliamps, it is quite possible that the entire system works for 100 hours, or it might even last for longer than that, as long as the internal battery leakage doesn't cause it to actually start discharging at that point, right. So, the alternative way of looking at it is, this number could be translated into a number like 1480 milliwatt hour, basically 400 into 3.7. Okay. Now, what that means is, like I said, if you were to actually consume 1.48 watts of average power, then it would last for about an hour. If you were consuming 1.48 milliwatts, you could probably have it running for 1000 hours. Now, is that the case? 1000 hours is quite a long time. It's several weeks of operation, right? In which case, it's quite possible that just internal leakage within this thing would have caused it to drain before you actually hit the 1000-hour mark. On the other hand, if you actually had 1.48 watts, it means you are drawing 400 milliamps continuously from this battery, which would probably not even last for 1 hour. Not only that, it would probably also affect the battery life, the number of times you are able to charge it and discharge it in future. Among other things, the heat generated would be much more than what it is normally rated for. On the other hand, for the system that we talked about, the 13.8 milliwatts of power, you could probably easily get something like 100 hours as a reasonable estimate. At least in that ballpark, right, in that range is what you can expect to see the battery lifetime. So, this kind of lifetime estimation and just estimating these values is a very important part of the design process, right, and being able to look at data sheets, estimate what the average power is going to be, and then actually making your choice of components based on that is something that can only come through experience, but is an important thing to sort of develop as you go further into designing systems. Now, of course, finally comes the question, how do you actually go about controlling power consumption, right? As we saw, there are some circuit centric choices that you can make, and the most important being the choice of components itself, right? Ideally, you pick a MCU that has many low power modes or whatever it is that you require. On the other hand, choosing a very complicated processor with a large number of low power modes might end up backfiring, because you don't even need all that many different modes. What you need is a simple processor that just does the task and still gives you enough of a low power mode that you are able to get the average power down. Things like display technology or the RF, the wireless communication technology, as we saw, can make a huge difference, right? Because those are typically, they have high active currents that they require, which means that choosing things that are efficient in that, for example, the e-ink displays that are there in the Kindle and various other kinds of devices, right? Or Bluetooth low energy as opposed to Wi-Fi, right? All of those can make a significant difference in terms of the energy required for actually operating on the battery. There are circuit level techniques such as clock gating, dynamic frequency scaling. You try operating at a lower frequency than the peak whenever possible, right? Shutting off peripherals that you don't need and so on, but these are usually not in your control. These have to be provided as capabilities of the CPU or the MCU itself. Power supplies are something that you do get to sort of choose. These are components that you need to pick. Typically, picking ones that are known to be efficient and have low leakage or other losses is a good thing to do. If you anticipate, there are again different kinds of regulators. There are what are called LDOs, low dropout regulators, versus the switching mode regulators. Switching mode regulators are typically more efficient, but on the other hand, they have other kinds of problems associated with them, including the digital noise that gets picked up with the system and so on, right? But it means that there are choices available to you, and you need to sort of understand the choices and decide on them. Now, having said all that, you also end up having a lot of software control over your power, and primarily it all comes down to that duty cycle number that we saw earlier, right? You can optimize your I/O basically by reducing the number of sensor readings, batching communication so that the turn on, turn off time, the duty cycle required is less, compressing data possibly if required or if possible, right? Using more efficient algorithms, right? Using a fast Fourier transform versus a regular discrete Fourier transform, using shift and add operations instead of multiplications, right? Reducing the amount or types of dynamic memory allocations that happen inside the system, right? And once again over here, the idea of using interrupts. In general, interrupts are going to be better than polling, right? Because hopefully you can put your system into deep sleep and reduce your duty cycle during the time that the interrupt is not active. But you need to be careful and make sure that you don't get too high a rate of interrupts, because that can end up defeating the purpose of using interrupts in the first place. Sometimes, in fact, you might find that if you have many sensors, then just by sort of waking up once a second, monitoring all the sensors and then going back to sleep for a second, right, is more efficient than having an interrupt coming from each and every one of those sensors, which in turn is waking up your CPU multiple times. Okay. So these are all things that you need to sort of understand all the implications, and the only way is to actually sort of do your performance estimates and practical experience with actually writing and building such systems.